now, Greg, and head it over to you.
Okay, well, great. Thanks for that introduction, Megan, and thanks for the opportunity for me to share this work. As Megan mentioned, this GTR that I'm going to present some information from was published in August, but the actual research I'm going to present today is actually more than a few years old, and I'll kind of describe as we go through what the timeline was. But it is still very relevant. There's a lot of work similar to what we did in this project going on, and so I'll refer to that throughout. So anyway, yeah, I'm just really happy to have the opportunity to share a little bit about this work. So here is the cover of that publication that we've mentioned. Rocky Mountain Research Station GTR 415, development of a severe fire potential map for the contiguous US. And my co-authors on that, as you can see here, Matt Panunto and Brett Davis, who were at the Fire Lab, they both moved on. Penny Morgan at the University of Idaho, Donovan Birch was with the University of Idaho at the time, he's now with the BLM, and Matt Jolly, who's also at the Fire Lab. And there were actually quite a few other people that worked on this project over the years who didn't end up as authors, but lots of people who I have to acknowledge, particularly Robin Silverstein and Jason Herink did a lot of the analysis work for the Western US part of this project. This project also has a little bit of a presence in a couple other places on the web. So at the website for the Missoula Fire Sciences Lab, which is firelab.org, we have a page about this project. And actually, what I'm presenting to you, the development of this severe fire potential map, was just one of several pieces of this broad FIRESEV project when it was first initiated back around 2009, I think. Bob Keene was the PI on the project. Penny Morgan was a co-PI, and I eventually became a co-PI as well. And the URL is there. And then we also have a presence on the FRAMES website hosted by the University of Idaho. So when we started to produce spatial products, raster data that could be downloaded, we chose, because a lot of this was through an agreement with the University of Idaho, to use FRAMES as a way to publish our spatial data. And I've got the link down here to that page as well, and you'll see it again in this talk. All right, so when I was putting this together, you know, I've talked about this project a number of times, but I wanted to start out by just using some pictures to clarify the concepts that we're talking about. Burn severity is something that we hear a lot about. Sometimes you'll hear it referred to as fire severity. Those terms can be used interchangeably. And I'm talking mostly about high severity fire, or I'll also use the term severe fire interchangeably with that. So what do I mean when I use those kinds of terms? Well, I think a lot of people, and especially lay people, think of this kind of picture when they hear about a high severity fire or burn severity or high severity. This is not a picture of severity. This is a picture of fire intensity, which is a characteristic of fire behavior. It's, you know, the amount of energy released by a fire. And so what we're looking at here is a high intensity wildfire, but we don't know anything about the severity of this fire necessarily from this picture. What burn severity is an ecological measure that describes the effect of wildfire on the vegetation and soil in an ecosystem. And so burn severity is typically something that's measured after the fire. If it's measured within the first, you know, short little while, maybe immediately after 2 months after, it can be considered what's called an initial assessment. Often it's evaluated 1 year post-fire, and so those are referred to as extended assessments. And so I'm going to show some pictures here, just examples of what that looks like in the field. Most of these pictures I'm going to show are 1 year post-fire. But I tend to prefer the term burn severity because it's a characteristic of the burned area rather than fire severity, which maybe could be construed as a characteristic of the actual fire environment during the fire. So let's look at some places, some examples of burn severity. So here's an example from Central Oregon outside of Sisters. Here's an example from Western Montana. And I think a lot of people have this kind of image when they think of an area or a forest that's had a high severity fire. Completely blackened trees, denuded vegetation and soil. And often there's not even a whole lot left in a high severity fire. And so here's another example from Western Montana. We also really wanted to deal with all different types of vegetation in this project, so not just forests. And so the same concept can apply in shrubs and woodlands, where in this case we've got some pinyon juniper in the foreground, some arid, semi-arid Great Basin shrublands on the foothills there. But if all the vegetation has been burned away, it can still be construed as high severity. Again, here's an example from the Great Basin in Utah, pinyon juniper woodland, all the bunch grasses burned away, starting to come back a year later. Here's an example from sagebrush steppe in north central Washington. Sagebrush, you can see the skeletons there, and a lot of the grasses had been burned away. Again, some recovery of the grasses. Here's an example from California, chamise shrublands or chaparral from the SHU lightning fire that burned in 2008. And also from Southern California, here's a Joshua tree woodland. Not something that I had seen pictures of very often until we actually did some plots in this environment. Also, this project is national in scope. So, I've been showing examples from the Western US, and that's what we tend to hear about, but burn severity is also something that people are concerned about in the Eastern US. So here's an example from Great Smoky Mountains National Park in Tennessee, where you can get high severity fire in oak and pine forests. Likewise in Virginia, Shenandoah National Park. And so we have examples of this from around the country. Typically, what I've been showing you are the effects on vegetation. You can see here we've got some resprouting and recovering happening a year later. But also severity captures the concept of effects on the soil. And so this is a picture from a fire in California where this stump probably smoldered and the root system associated with it smoldered for a long time after the flaming combustion was over. And the result of that are these tunnels in the soil where it's essentially been sterilized. So when we measure severity in the field, we're thinking about all of those very fine scale changes to the soil and the vegetation. For this project, we wanted to back out and think of it across the landscape as a spatial phenomenon. And we wanted to see, could we use characteristics of the landscape? So topography, some type of maps of vegetation, some broad climate indicator that might help us to understand the types of sites that are more likely to experience in high severity fire, and then use that to create predictive models. So why focus on high severity? There are a lot of really great studies on burn severity that actually look at sort of the continual metrics of severity and how the statistical distributions of those change through time. And those are great. For this, we wanted to really focus on high severity because that's where the effects tend to be most pronounced and areas that tend to cause the greatest concern. And so, high severity fire is certainly a natural part of a lot of ecosystems, but we are seeing a rise in it across the landscape. So here's an example of a very recent paper by Sean Parks and John Abatsoglu, where they were able to demonstrate using data from 1984 through, or 1985 through 2017. They were able to show that many forested areas throughout the Western US are seeing a several-fold increase in the area burning with high severity. And so that's significant ecologically. That's something to be concerned about and to understand a little bit better. So that's one study that's come out very recently. Like I said, this is super timely, and the fact that Megan, keyed in on the GTR publication right around this fire season, just a small sample of a couple other very recent publications related to this topic. So, why does high severity matter? Well, it could be leading to conversion of certain Western forest types, especially under a warming climate regime. Here's another example of that same type of question: fire catalyzed vegetation shifts in ponderosa pine and Douglas fir forests. And it's also making its way into more popular media outlets. So Crystal Colden is a pyrogeographer, as she calls herself, or a fire scientist, but she wrote this piece in Bay Nature, which is a publication in the Bay Area for the general public. Size isn't the best way to talk about fires. We need to be thinking about other ways to catalog and measure fires that give us more specific information than just how big it was. Likewise, NPR ran this really great story this fall. Same thing, 4 million acres have burned in California, but that's the wrong number to focus on. We need to be looking at what are the measures that will tell us about the impacts of the fire, not just how big it was. Okay, so with that background, here's a listing of the objectives for this FIRESEV project that we had. So number one, we were charged with developing a comprehensive map of the potential for high burn severity for all areas in the contiguous United States using empirical observations and statistical modeling. So we'll talk through how we did that. Then secondly, we wanted to evaluate the quality of the map that we were able to produce so that we could provide managers with some guidance on its interpretation and use. And then lastly, and more broadly to sort of the scientific community, we wanted to contribute to our understanding of what factors drive the occurrence and patterns of high burn severity. Okay, so diving into our study area, which was the contiguous United States. This actually came about as two separate projects. And so the first part was just the Western United States, west of that bold line that you see on the map. And that was funded by the Joint Fire Sciences Program. It was an agreement between the Forest Service, Rocky Mountain Research Station, and University of Idaho. And so that's where a lot of those collaborators I mentioned earlier came in. And the goal was to do what I've been describing for the Western United States. What made it a little bit unique was that we were trying to do it for all lands, not just forested areas. There are a lot of studies that look at burn severity of forested areas in the West. We wanted to try and do it for all lands across the Western US. And then the way that we organized the study was by these mapping regions that you see on here. And so we had 17 mapping regions originally in the Western US. They're basically taken from existing ecoregion maps and classifications with some areas grouped and some minor lines redrawn, but basically ecoregions with similar fire characteristics. And then in the Eastern US, that project came along later. So we actually finished up the West back in about 2013. And then the East in around 2014, the Wildland Fire Management RDNA, which is also part of the Rocky Mountain Research Station, Tim Sexton came to us and said they'd really like to include it in decision support tools like WFDS. And so they funded us to complete the project across the Eastern US. So that, as you can see, wrapped up in 2016. So like I said, the research itself has been done for a while. It took a long time to document it all. But these mapping regions are how we organized all of our modeling work. And then the little squares or rectangles that you see on here are 1 degree by 1 degree latitude, longitude tiles, which we use to manage all of the data. So we did all of our actual sort of data predictions spatially by those 1 degree tiles. There are over 1,000 of them across the US. A little note about the inset map up here is just how we went about selecting the fires to include in the models for a particular region. And so we used the footprint of those 1 degree tiles, and any tile that touched a region, we used fires from that tile. And part of the thought behind doing that was that we wanted to minimize seam lines once we put all this stuff back together to make a national map. And so a number of fires, as you can imagine with that kind of approach, end up being in the model for multiple adjacent regions. And yeah, the hope was to reduce seam lines in the end. All right. So another note about how we organized our study. We realized pretty quickly that severity is something that is very context specific. And so we needed to think about it differently in forested settings versus non-forested settings. Like I said, a lot of research is focused on severity in forested regions of the West, and there's a reason for that. There's a lot of data. The severity concept is fairly straightforward. It gets a little bit tricky, and we had lots of conversation and debate about how to define severity so that they'd be comparable across all vegetation types. But we decided to do all of our modeling work and then predictive mapping separately for forested versus non-forested environments. So to do that, we leaned pretty heavily on some of the land fire data sets. We needed two different types of forest, non-forest masks. One was for current conditions for doing our predictive mapping work. And so for that, it was fairly straightforward. The land fire existing vegetation cover raster actually produces or provides a really nice medium for doing that. We selected out basically anything with forest cover or tree cover greater than 10%, and that became our forested area. And then the inverse of that is the non-forested. We also wanted a map that would attempt to depict what conditions were before any fire in our sample. And so we had fires that went from 1984 all the way up through 2013. And so to try to go back in time and get at what the site was potentially before the fire, we used a combination of layers. The land fire environmental site potential, which is one of their potential vegetation products, was really useful. And so we used areas where the site potential is mapped as forest, even if it's not forested today. We also used a data set that was developed in conjunction with the land fire program to help inform actually a lot of the mapping efforts that happened between the original land fire mapping and the sort of rapid refresh and refresh products that happened subsequently. And that's this Landsat time series stack vegetation tracker, which basically was exactly what that said. It was a stack of Landsat images where forests and non-forests were mapped and then characterized. And there was a characterization in there of areas of persistent forest. And so we used that to help inform that map of potential pre-fire conditions. And then also the land fire existing vegetation cover helped to inform that pre-fire forest, non-forest mask. All right, so that gives you the background and the setup. I'll walk through in a very high level the methods that we used. And so this flowchart kind of gives you an overall sense of what the process was. And if any of you are familiar, again, with processes used by land fire to map their vegetation products, whether it's existing vegetation type, potential vegetation in terms of the environmental site potential or biophysical settings, it actually looks a lot like this. And that's no accident. I did work for the land fire program from 2004 to 2009, and I did potential vegetation mapping work for land fire and had gotten really familiar with a process that looked very much like this for mapping vegetation. In that case, we used classification and regression trees similar to what we did in this project, different software, but very similar concepts. So the overall flow that we followed, the first phase had to do with just acquiring all of the data that we needed to evaluate burn severity across this broad of a spatial domain. Compile that all into a database that we could feed into modeling software, create these classification and regression tree models, then apply them to new comprehensive spatial data sets that would allow us to map out the predictions across the landscape and produce maps of potential fire severity or burn severity. And then finally assess the quality of those maps so that we could give some recommendations. So we'll step through this process with a little bit of detail here, particularly in the first parts. So to acquire the data, this project was built on the Monitoring Trends in Burn Severity project, MTBS. And we really could not have done an effort of this size without MTBS, because they had done the work of cataloging all large fires that had burned in the United States from 1984 up to the present. And so at the time, I think for the West, we included through, I want to say 2007. And every large fire, so that's greater than 1,000 acres in the West and 500 acres in the East, is mapped using pre and post fire Landsat imagery, and these indices of burn severity are calculated. So we're looking here at a map of the relative difference to normalized burn severity, or RDNBR. And then those can be categorized using thresholds, like you see here, into these unchanged low, moderate, or high burn severity areas. Those thresholds are usually calculated using correlation with field measured plots. And so here, you can see examples. This is a fire that we measured plots on. And so these are two of my field photos of, a high severity area on the top and a moderate severity area on the bottom. So anyway, we had this available to us for the country from MTBS. So that's how we acquired our severity data. And you can see here in this map, ultimately we ended up between East and West acquiring over 12,000 fires and quite a few more in the Western US, especially covering a larger area. But there we go, yeah, 1984 to 2007 for the West and 2000 to 2013 for the East. And as I mentioned, field plots were needed to do the correlation of the satellite-derived index to field measures so that we could do the classification of severity. And to do that, for this project, we actually collected about 500, actually over 500 plots. And so those are the ones with the little blue triangles on the map here that were collected for this project. And then basically I begged people who were doing similar work to share their data, and we were able to compile ultimately over 3,600 field plots across the West and the East. Of note, I have the URLs on the bottom of the screen here. The CBI plots that we collected just for FIRESEV are available through the Forest Service Research Data Archive. And then just within the last year, Josh Picott, who is a contractor with USGS and has worked a lot with MTBS, compiled a comprehensive set of CBI plots from a number of researchers across the US, and that's published here through the USGS Science Space website. Okay, so that's our predictor data, is all of the burn severity observations. Because our focus was on high severity, we needed to process that. And for the West, we chose to use the RDNBR as our index of choice. We thought we would use that in the East as well. And as we got into working with the data in the East, we realized a couple things pretty quickly. One, in the East, they actually prefer DNBR for a number of reasons, which is just not the relativized version of the index like the RDNBR. And they do a lot of assessments, what they call single scene assessments with just a pre-fire NBR or normalized burn ratio. And so we had to adjust our methods a bit when we got to the eastern part of the project. The other thing that's notable in this graph is when we graph it out like this in terms of the percent of area mapped in low, moderate, and high burn severity by these different indices. We've got the West in the top graph and then the East in the bottom two. You can see that the West has quite a bit more high severity, and the East, the DNBR images have some high severity, but the single scene NBR images have almost none. So because of this, we actually made the choice. We had already completed the work in the West where we were modeling the potential for high severity. In the East, we decided to group moderate and high together. And so we're really predicting the potential for higher severity, which is that combination of moderate and high in the Eastern US. So we converted all of the data for the different fire areas to binary severity. So in the West, that was high severity versus all others. In the East, that was the moderate and high grouped together versus low. Then we took a 1% sample of those burned areas. And so it's 30-meter pixels. Of those pixels, we selected out 1% of them, and we used spatially balanced and methods, and also balanced the sample based on the response, the two categories of response. And so that led to a data set of over 2 million sample points across the West from those burned areas. So that's our predictor data. As the graphic says here, we needed to create a spatial data stack of predictor and response. So I'm not going to get into the details of this for time's sake, but I've talked to you about the burn severity data we used for topography. We drew on the 30-meter national elevation data set, which was the best available DEM or elevation data at the time. We calculated solar radiation using slightly different approaches in the west and the east as one of our topographic variables, and then a whole suite of 11 other topographic indices that you can derive from a DEM. For vegetation data, we used the normalized difference vegetation index, which is a measure of vegetation, the amount of green photosynthetic vegetation. It was available in the West as part of the Landsat data delivered with MTBS. In the East, we chose to use MODIS instead, which is a coarser resolution, but there were a number of advantages to using MODIS in the East. So a little bit of variation here from west to east, but NDVI in both places. And then for fuel moisture, this was where we consulted with Matt Jolly, talked a lot about some of the various indices we could use to represent climate or drought or general weather conditions at the time of fire, and settled on using this index of 1,000-hour fuel moisture. If you're familiar with fuel moisture, a low fuel moisture means that it's very dry, which means you generally have high fire danger. We flipped that so that in referring to, say, 90th percentile conditions, we were actually referring to 10th percentile fuel moisture, but to put it in terms that are similar to the way that fire practitioners are used to talking about fire, ERC, energy release component, is another metric that they're very used to talking about in terms of 90th, 95th, 97th percentile. So we used a 1,000-hour fuel moisture index. So with all of those various data sources, we then had to produce a database, basically giant data tables, at all of those 2 million sample points with the input values of our predictor and response variables. The key here is that we had data for burned areas only here. We didn't need data for the entire landscape. And so we had, like I said, that binary severity, which is different in the west and the east, and our suite of predictor variables for topography, vegetation, and fuel moisture. So with all of that, then we could feed that into our statistical models. We chose to use the random forest classification and regression tree model implemented in R, and we used 1,500 classification trees. So random forest gets its name because it is a forest of classification trees. Actually, it has nothing to do with forests as we know them. And then we developed a process by which we would run a model for, or including all of our input predictors, and then subsequently remove the lowest performing predictor and run the model again and find what we referred to as our optimal model, which had a reduced set of predictor variables, eliminating redundancy, but achieved the lowest classification error. So we did this separately for every one of those mapping regions that I showed you, and for forest versus non-forest. So a total of 50 different modeling scenarios. We developed an optimal model, and then what we got out of that were statistics on overall model performance, on variable importance, which tells us about the influence of the different predictor variables on the outcome, and a predictive object, a random forest model object that we could use to do the mapping work across the landscape. If you're interested in learning more about the details of our random forest process, it's actually described in this publication that was done as we were doing the development work for this project back in 2011, published in Ecosphere. So then with our random forest model objects, we could take that and apply it to a raster spatial data stack of predictor variables covering all areas. So not just the burned areas. Now we need data covering the entire landscape. And each pixel is treated as a new case, run through that classification tree, and predictions are produced. So in this case, we needed spatial data that was comprehensive. And we needed to be able to represent the landscape for which we wanted to do predictions. So topography was static, at least within our timescales. And so we are using the same topographic inputs that we used to create the model. Vegetation, we used NDVI again, this time from MODIS for both the west and the east. For the West, we used 2011 as our prediction year. For the East, 2014. And then for fuel moisture, basically what we did was set a constant value across the landscape, and we ran the model or the predictions actually at 3 different levels, 80th, 90th, and 97th percentile. Ultimately, we chose to just choose the 90th percentile as our map to deliver. So in that process, every 30-meter pixel is classified by each of those 1,500 classification trees, and you get predictions of whether that pixel is likely to be high severity or not. So some graphics to sort of illustrate that. Here's a little map area. Our scale goes from 0 to 100. It's the percent of times that a pixel was predicted to be high severity or higher severity in the East. And so here are a few example calculations. So here's an area that is orange on the map. That pixel would have had, out of 1,500 trees, it would have been predicted to have high severity 1,245 times and low severity, or I should say not high severity, 255 times. So you do the math, comes out to 83% of the time it was predicted to have high severity. Similarly, a moderate area, an area that's sort of yellow or greenish on the map, 840 out of the 1,500 times, which is 56%. And then a blue area on the map. So 330 times it was predicted to have a high severity outcome, and so 22%. One important thing to note about this is that even in this case where it's mapped as a lower likelihood, it's 22% on a 0 to 100 scale, it was predicted to have high severity 330 times. And so just because a place is blue on this map with this kind of color scheme doesn't mean that it can't have high severity. So we really were trying to predict the likelihood of high severity across the landscape. All right, so quick recap of that flow chart. We walked through all of the steps involved in phase 1, 2, and 3, at least from a high level. And the details of all of those steps are in the GTR if you want to know. And then lastly, we needed to assess the accuracy of the map. And I'll get to that as we kind of talk through the results, and I'll show you how we did that. Okay, quick sip here. All right. So walking through some of our results, I'm going to start with random forest model performance. So this just has to do with how well did our statistical models perform in each of the 50 different modeling scenarios. So you have here again the map of our regions for some context and reference, and then a table of the modeling results for forest models. And so we've got regions down the first column here. The west is everything above the line. The east is everything below the line. You can see the number of fires and sample points used to build our models in each region, and the number of predictors included in the full model. So that's the full suite of predictors. And then using that process I talked about to select the optimal model, you can see we always ended up with a smaller number of predictor variables in our final optimal model. And then the two statistics that we tracked were percent correctly classified, or PCC, and area under the curve, which is a common accuracy metric. Interpretation of that AUC metric would be anything greater than 0.7 should be considered fair. Anything greater than 0.8, good, and greater than 0.9 would be excellent. And so just a quick perusal of these numbers, you can see from our modeling output, and these are cross-validated model statistics. Generally, our models performed at least fair, often good, and in some cases even excellent, with percent correctly classified, often in the 70+ range. So for a phenomenon as complex as burn severity, we felt pretty good about that. Here's the same statistics for our non-forest models across the 25 regions. I will just jump back real quickly to the forest ones and point out that as we got to some areas of the East, in particular region 25, which is up here in northern New England, we just had almost no fires to work with. And so I would not put a whole lot of stock in our outputs from a model built on 7 fires for forested environments. And for non-forest, we had so few and actually no sample points in non-forest environments up there that we couldn't build a model. That was the one case in which we didn't succeed in building a statistical model. But again, for non-forest, we see the same range of values in the PCC and AUC metrics. So here's a look at the map. This is the SFP, or severe fire potential map, for the Western US. When we plot out those percentages of times that each pixel was mapped to be high severity. And then those are available as raster data products by region and by forest versus non-forest. And that's on the FRAMES website. Here's a look at the Eastern result. So the map for the Eastern US, again, I noted that region 25, this is only the forest model built on very little data. We were not able to do a non-forest model up there. But the data, again, are downloadable via FRAMES on the FIRESEV East page. So quick look at the statistical distribution of those values. One thing that was interesting is that they tend to be below 50. Values above 80 were extremely rare. And so on the 0 to 100 scale, they generally tended to be pushed towards the left side of that scale. And quickly looking at the mean value, when we look at just broadly all data collectively for the west forested areas, west non-forest, east forest, and east non-forest, and we can see that the means are, in the 30 to 40 range. Then we did do some evaluation of what those patterns look like at a region by region perspective, and even breaking it out by different types of landform classes. And the hope here gets at that third objective that we had of trying to provide some insight into places that maybe are more likely to experience burn severity. So we're not too worried about the statistical significance of any of these relationships. We're really sort of standing back and squinting and saying, what can we say from a very general perspective about where we tend to see high severity fire? So real quickly, we have the average predicted value across all landform types by region, and that was 41. But then when we look at different landform categories of flat landscapes, warm slopes, cool slopes, and ridges, the cool slopes definitely had the highest average predicted severity value. So just as an example to kind of follow through how we could talk about that then on a in the context of geographic variability, if we look at mapping regions within the middle and northern Rockies, so I've got them circled on the map here and highlighted in the graph, you can see that particularly when we look at that graph of the cool slopes, they tend to be quite a bit above average relative to the other mapping regions. That makes sense when you think about where forests tend to get dense in these Rocky Mountain environments. It's on those northern slopes. And so when they get dry enough to burn, there's a lot of fuel to burn. So that makes sense. An exception to that pattern of cool slopes having the highest severity is in Southern California, the Sierras and the Great Basin, where actually there it looked like cool slopes generally tend to be about average, but all of the other landform settings tend to be above average in those three map zones. And then in the Southwest and the Southern Plains, so we can see on the map here, they tended to be consistently lower than average across all of the landform types, which again, maybe isn't too much of a surprise when you think about ponderosa pine ecosystems and other Southwest and Southern Plains ecosystems that maybe do tend to burn at low to moderate severity. So, the results seemed somewhat intuitive. We see sort of reinforcement of what we know about geographic variation. And let's see, then looking at the Eastern US, slightly different patterns. So here, looking at the different landscape or landform types, the ridges definitely had the highest predicted severity or likelihood of severity. And then when we key in on a few regions, we can see the Great Lakes region in particular tended to have higher values on both warm slopes and cool slopes, as well as ridges. And in the Appalachian region, we tended to have higher predicted SFP values on warm slopes and ridges. Again, those things make sense when you think about the ecology of the forests in particular that tend to burn in those regions. And then the central and eastern plains had consistently low SFP predicted values. Again, probably similar to what we were seeing in the neighboring Great Plains region in the west. So that's just an example of how we could take a look at the spatial variation using patterns in the predicted severe fire potential index. Another thing that we did as a sort of corollary to that was looking at patterns in MTBS data themselves. And so this is the mapped burn severity observations from MTBS categorized to high severity or not in the West. And here what was interesting to note was that both for forests and non-forests, the average percent high severity as observed and mapped is about 33%. Now you can see there's definitely some variation around that number from region to region, but on average about 1/3 of burned areas maps as high severity. That's interesting. A little bit of variation with landform types, but not a lot. So I'm not going to get into the details there. And then this is a look at the eastern US. Here, similar to that graph I showed you earlier, we definitely can see that the average percent of higher severity, so now we've actually got moderate and high grouped together, is still quite a bit lower in the eastern US. So the average value for forest across all landform types is about 20% of burned area in the moderate to high classes, and about 10% in non-forest areas in the moderate to high classes. So quite a bit less high severity and even moderate severity in the eastern US as observed. All right, so one other way that we evaluated our map products then, we've talked about how we looked at the statistics for the model, but how did we evaluate the map itself? To do that, we took a stab at converting our predictions basically over to a binary map that we could compare to the binary version of severity mapped by MTBS. And so what we wanted to do is, like it says here, ask that question of how often were our predictions right? When we drew the original pixel sample that I mentioned earlier in the talk, we held out 10% of that as a validation sample. And so we used that for this purpose. And because we were doing predictions, as I mentioned, with the 1000-hour fuel moisture index set to a constant 90th percentile across the landscape, we only selected fires for this validation that actually burned between the 85th and 95th percentile of that index. So, we're looking at an example of one fire here on the right in this map with the severe fire potential index mapped. And what we wanted to do was basically ask the question, how could we convert that over to a binary map of high severity or not and compare it? And so to do that, we tested a range of breakpoints from 25 to 75 on that scale that you see there. So here's an example of just using 50, which would be sort of the intuitive, just break it right down the middle. So every area that's mapped with an SFP value above 50 is shown in red, and then compare that to the binary severity from MTBS and ask how often they agree. So here's the binary severity mapped for that fire by MTBS, and then overlaid. So the observed severity is in gray. Our 50-50 split is in red. And so we would be asking, what's the agreement between those? This one actually doesn't look that great. So when we did that, here's a quick look at the results. As I mentioned, we tested a range of breakpoints. The best breakpoints generally were lower than 50. Sometimes they were around 50, but generally lower. And then we took the breakpoint that provided the best agreement and again tracked the AUC and PCC statistics. And unfortunately, what we saw was that our model results showed that our AOC values were almost always above 0.7. This validation gave us the opposite, that our AUC values were generally under 0.7, and our percent correctly classified were usually between 50 to 70%. For a binary prediction, I wasn't that thrilled with that result. But I'll kind of put a little I'll soften that a little bit in a minute here. Same points with the non-forest results. So again, our AUC and percent correctly classified showed lower performance than what we were getting out of the random forest model statistics. So that's at a pixel level, how we would interpret the mapped values. So keep that in your mind for a minute, and we'll get back to that in a second. One other way we looked at the results was the importance of the different variables. I mentioned we wanted to be able to say something about the drivers of severity. So again, just very cursory look at that. Looking at forest models for the West, we found that elevation, vegetation, and fuel moisture in that order were the most important variables. In the East, same three variables, but different order. Their fuel moisture was most important, and these are the forested models. For the non-forest models, in the West, vegetation, elevation, and fuel moisture. And in the East, again, fuel moisture, excuse me, was the highest or the most important variable. All right, so to kind of bring this all together, what can we draw from all of this work? What are our key findings? First off, we definitely, I think, can conclude that burn severity is a complex phenomenon, and that evaluating it across ecosystems and across the entire United States like this, or at least the contiguous US, requires a lot of flexibility and adaptability. And you saw that in some of the variation in methods that we used from east to west, different data sources, et cetera, context of forest versus non-forest, all of that. And that affects our ability to model the data. Oh, sorry, I'm getting ahead of myself. The data are very noisy, for sure. And then the availability of burn severity data is patchy. And so as you saw from the maps of the burn severity data from MTBS that we drew from, there are large areas, particularly in the eastern 2/3 of the US, where we really just don't have data to build models from. And so that definitely influenced our ability to have solid modeling results in some places. In terms of the effect of different variables, vegetation, topography, and site-specific fuel moisture definitely affects severity, and I think we can say that from our results. We found the topographic variables to have some importance, and as you saw, elevation was always in the top 3, but they could be acting as surrogates for vegetation distribution. NDVI, which we used for vegetation, captures one aspect of vegetation, but not everything. And so other studies have found that when you have more specific, more precise data for vegetation, that often will overwhelm the topographic. So we could be seeing just some effect of vegetation distribution in our elevation and other topography variables. Fires can burn hotter where there's more fuel, especially in the West. And so we saw that with NDVI being an important variable where we have a higher density of vegetation that can burn. So the example I showed a little while ago of the North Slopes, for example, in the Northern Rockies, tending to have a higher occurrence of burn severity. That makes sense ecologically. And our results support that. And then looking at the East, fuel moisture was the most important variable, which you could interpret to sort of support the concept that severity in the Eastern US is climate limited. So there, fuel may be available in most places, whereas in the West, it can be a lot patchier, but only under the right conditions, when it's hot enough and dry enough, do you get fires that produce high severity results in the East. So those definitely have implications, all of those, for how we might consider burn severity in terms of management options and in terms of, in the context of climate change. So continuing some findings here, independent validation is definitely important with this type of modeling and mapping. So our model performance results definitely indicated models that performed reasonably well. Our validation results maybe countered that a little bit. Now, I said I would soften that a little bit, and my point with that is that that's if you zoom into the pixel level and you're trying to interpret the map that we've produced as being accurate at that fine scale. I still think that when you, as I said earlier, sort of stand back and squint and look at the general patterns, there's a lot of value in the predictions in our map. So key finding number 5 here, high burn severity occurs in a relatively small portion of burned area. And so I showed this statistic a minute ago that about 1/3 of burned area in the West and much less in the East has high severity. That's significant. We hear news reports, and I referred to those articles earlier, that size isn't the best statistic to use, and yet we hear fire talked about as destroying all these acres, when in fact a lot of those acres are burned with less than high severity, and maybe experiencing very beneficial ecological effects. Also, the proportion of high severity relative to the total area burned generally tends to be stable over time. Now, that's not true in all regions, but that Ecosphere publication that I authored in 2011, we definitely found that to be true, that proportion of about 1/3 of the area burned at high severity hasn't changed a lot in some regions over the last 25+ years. But point C here is also important, that as the overall area burned increases, so does the area burned with high severity. And that article that I referenced earlier by Sean Parks and Chana Botsoglu does a really good job of documenting that. And so that is something to be concerned about, that we are having a lot more area, even if the proportion isn't changing, we're having a lot more area burning with high severity. And then lastly, I don't know if you can consider this a finding or not, but data from our work from this project has definitely contributed to ongoing studies of severity. And so I just have to throw a little shout out here to Sean Parks and his colleagues on this next generation fire severity mapping project. And this is actually a link. If I share the slides, you can link to it. And Megan, maybe you can throw that in the chat too. But they actually have used a lot of the data that we assembled as predictor data for this project and taken everything a step further. And so really developed a little bit more sophisticated way of doing the modeling work, bringing in data that we were missing, like correlating to the day of burning. Yeah, I won't get into the details of it, but they've moved it a step forward, and I feel like our work helped to kind of lay the foundation for that. And lastly, this is my last slide here, bringing it back to what does this mean for managers? How can they use the information that we developed from this study? So we have these 4 points in the GTR, and they're expounded upon a bit more in the GTR. But first off, just understand that the best use of the maps that we produce for this project is for long-term assessment and strategic planning. They should not ever be used to guide tactical decisions. They're just not specific enough, not tuned enough to the conditions of any specific fire to use them to guide tactical decisions. Secondly, the strength of this map that we've produced is really, as I mentioned, in the generalized patterns in potential severity, and not so much in how a specific pixel is mapped. So keeping that scale and that context in perspective when looking at these products is important. Third, the index represents the likelihood of high severity or moderate and high severity in the East, but it says nothing at all about the likelihood of low severity fire. So you can't interpret our 0 to 100 scale as a surrogate for a burn severity scale. Just because something's mapped, say, as a 20 on our map doesn't mean that it's likely to be a low severity fire. We didn't model anything about the likelihood of low severity fire. And then fourth, we do feel like this map could provide a starting point for managers who are interested in implementing fuel treatments to moderate severe fire potential on their landscapes, to think about their landscape as a whole, but it's not detailed enough to guide specific placement of treatments. So with those last words about implications, I'm done, and I will thank you for being here and for listening. And I haven't left much time for questions, but we'll probably take a few.
That's okay, Greg. No worries. I got a couple queued up. So, Chris, I think you did cover this, but I'm forgetting, so I think it might be wise to clarify. Why did you use RDNBR in the West, but DNBR in the East?
That we could probably spend a whole hour talking about, but it was 2 separate projects. In the West, And I do actually, I'm a real believer, particularly in the Western US, that the relativized version of those burn severity index are superior when you want to compare severity from fires across a region. The absolute index of DNBR is great for looking at one specific burned area, but when you want to compare fires across a region, the relativized indices are better. We wanted to do the same in the East, and there were just a number of reasons why it just wasn't practical to do so. And yeah, unfortunately, I don't have time to really get into it. And I'll be honest, it's been long enough. I don't remember all the factors involved, but I know there is some information about it in the GTR.
Great. I put the link in the chat window to that. And if folks could hang around for just a quick minute and take our evaluation poll, that would be awesome while we get through some of these questions. Chris asked another question. Did you use the MTBS classification of high, medium, and low? Their RD-NBR or DNBR thresholds for classification levels of severity can vary among fires, even within the same vegetation type or national forest. Did you create your own threshold values?
Yes, we did. And there's a ton of information about that in the GTR. I just didn't have time to cover it today. So yeah, and actually the way that we thresholded in the East was quite different. So I encourage you to check that out. There's a lot of detail on it.
Perfect. Michael asks, with RAVGR models, there has been discussion about accuracy versus ground truth results due to effects of RD-NBR overestimates in high reflectance soil areas. Did you encounter the same issue with your project?
I don't think so. So I think with that question, the Ravage products are, sort of immediate post-fire. We did not use any of those products in this project. We were using all MTBS. And because we really sort of outsourced all of the actual remote sensing work to the MTBS program, we didn't get too much into the technical details of the remote sensing piece with this. We used their products.
Arid system, Chris asked another question. Arid systems, particularly shrub and salt deserts, do not have a lot of 1,000-hour fuels. You didn't include those in your test of the model. How did you validate the models in non-forested systems?
Sure. So the 1,000-hour fuel moisture variable is something that's used in fire danger, which is the same sort of suite of information that ERC and other metrics like that are used in. Even in places where there are no 1,000-hour fuels, it's a metric that kind of incorporates the precip that an area has gotten within the last I can't remember how many days, however many days 1,000 hours is, but it's just a good overall indicator of drought, basically, and moisture conditions at a place, regardless of whether you actually have 1,000-hour fuels.
Inga asks, should we be encouraging folks in the Northeast to collect CBI data?
Absolutely, and that's something that we, kind of pushed in this GTR, is that I think in a lot of these places where we're missing information, we definitely need more field data collection, more, MTBS only looks at fires smaller than 500 acres in the East, and there are a lot of fires that burn in the East that don't reach 500 acres. So, there certainly could be a lot more detailed work done. And so absolutely, yep.
Great. Okay, last question, unless anybody else chimes in here. Phenology can tell you a lot about potential vegetation. Annual and perennial bunch grasses are active at different times of the year and have different effects on fire spread, area, and potential ecosystem changes. How did you deal with identifying vegetation in non-forested system phenology, where NDVI and phenology cues change several times a year, i.e. sagebrush steppe bunch grasses versus cheatgrass and reduce ahead invasive annual grasses?
Yeah. One thing I didn't mention about the NDVI and 1,000-hour fuel moisture variables was that they were time sensitive or temporal sensitive. So we, in the case of building the model, we were pulling from the pre-fire situation. And with the West, we used whatever the timing of that pre-fire image was, which was often Well, yeah, it varied in terms of how far before the fire it was, but usually during the growing season. And then for our predictions, we actually looked at, for every one of those tiles that I showed you, the 1-degree tiles, we looked at what is the most likely month of fire occurrence. And we used the NDVI from that month as our input to the predictions. So we were trying to predict for conditions that tend to see fire most often.
Great. Melissa has one final question. Even given the limitations you mentioned, do you think the results could be used for estimating or describing effects for NEPA documents?
Gosh, I don't know. I think just knowing everything that weighs on NEPA documents and that they can be challenged legally, there's a lot of noise and a lot of uncertainty in our data, and I'm not going to sugarcoat that. So I would be a little bit leery about summarizing the raster data and then putting that into NEPA documents. I think taking some general patterns and information from it would be useful, but there are other ways that you can get at similar information, I think probably for NEPA.
She also mentioned that rough models for Virginia showed heat load index to be significant. Did you see this in your work?
Gosh, yes, heat load index was definitely one of our topographic variables. And I don't have time to kind of flip back to the variable importance slide, but it definitely, I think, did tend to be significant in certain mapping regions. I don't remember specifically about Virginia, but yeah, it definitely was one of the more useful topographic variables.
Awesome, Greg. Thank you so much. If you're willing to share your slideshow with me, I'll host it on our website and put a link to that. So folks, please subscribe to our YouTube channel, our Landfire YouTube channel, and stay tuned. I'll post this recording within the next day or two. So all of the links that we might have overlooked or you might not have grabbed from the chat window, you can do so and reference those. So thank you so much, Greg, and thank you attendees for joining us. If you haven't taken the poll, the 2-question poll on your screen, please do so really quick before tuning or signing out today. And I wish everybody a wonderful holiday season from the Landfire team, you especially, Greg. You've been a huge part of our last 8 months of webinars that we've contributed to, and I just really appreciate you. So have a great day. Have a great day, everybody. Bye.